So let's start today's lecture. Hello, good evening, everyone. Uh, Today we will discuss the course content and some questions related to the assignment 9 of the course D09 of week 9. So in this week, actually, most of the thing like the state space thing I had covered in the last live session. In this session, I will mostly cover the few basic questions related to board plot. So I guess you might have gone through the lecture series by Professor Ram. So it will be helpful to get along with the course if you have gone through that. So without wasting time, let's jump into the first question. So here what I have taken two transfer functions. One, can somebody just tell how many poles and zeros each system has? Like how many poles and zeros P1 has and how many poles and zeros P2 has? So you have come across all the 9 weeks. So this is very basic question. Can I expect some answer from you, Ishan? How many poles the question one has poles and zeros, and P2 transfer function has poles and zeros. How many poles and zeros? Mm, Okay, then actually the thing is that okay, the first one, Ishan, the first one has one pole and no zeros. Very good, and the pole is at s is equal to minus half. Okay, okay, and zeros, it has no zeros because there is no expression in the numerator. And similarly, in the denominator, sorry, in the second transfer function, it has only one zero. It has no poles. Okay, so what are the questions? The question says find the respective corner frequencies, find the magnitude to the sinusoidal input, and the phase. Okay, so what we will do first, let's recap what is a corner frequency. So can somebody say in a board plot, like the board plot we draw, I'll just make it a little thicker. Okay, so in a normal board plot, what is the x-axis unit and what is the y-axis unit? Can somebody just tell? Because this is a very important concept when we go from till now, when we used to analyze in the time domain, it used to be t, and it used to be some mod of xt or something. Okay, the transfer function magnitude or something, it is t, so it's linear scale. But when you enter into the frequency domain, you need to analyze for a larger frequency. So that is not possible if you take a linear time scale. So that's why we have to take logarithm scale. Okay, log 10 base, and here the magnitude is 20. It's a dB scale on the dB scale. Okay, dB is like 20 log some x base 10. Okay, you need to understand these things. Okay, so what happens? What is the corner frequency? So any transfer function behaves in two ways most typically. One is in low frequency range and another is in high frequency range. You must understand all the board plots what we plot, that is an approximate diagram. Okay, it's not the exact diagram, and the approximate diagram is approximate enough, like it's fair enough to analyze the whole system. So where if this is the low frequency, because the frequency will be less here, this is the low frequency and this is the high frequency. This is the low frequency and this is high frequency. Low and high I am considering with respect to this. Okay, so it grows with 10 to the power, like powers of 10. Like this will be 1, then the next scale will be 10, then the next scale will be 100, like that. Okay, so where the low frequency and high frequency meet, that is called the corner frequency. Okay, so let's try the first question. The first question says my P1 of S is equal to 1 upon 2S plus 1. So remember, when we are doing the frequency analysis, generally S is equal to, we take a real plus j omega. Okay, this is responsible for damping. Okay, and this is pure frequency. Okay, omega is pure frequency. When we do the frequency analysis, we drop this, we tend it to 0. So whenever it's the frequency analysis, then we have to take S is equal to j omega. Okay, then what I can write, P1 of j omega is equal to 1 upon 2 j omega plus 1. Okay, so the magnitude, what will be the magnitude? The magnitude will be the magnitude of P1 of j omega. This will be 1 upon root over, because I can, in a normal real and complex, if this is the real axis and this is the imaginary axis, so 2 j omega plus 1, I can write like 2 in the real axis, 2, 1, sorry, 1 and 2 in the imaginary axis. So this is the kind of vector. So this is the point actually where this 2 j omega plus 1 lies. Okay, so the magnitude, this is the magnitude will be x square plus y square simply. So 4 omega square plus 1, correct? So now look at, so in low frequency, what happens, when the frequency is less, like like less, low means very low, like it's 0.1 hertz or 0.001 hertz. So this kind of frequency when we are talking about, then what happens when the square, anything less than 1, the square will be lesser. So we can say 1 is much greater than omega square for low frequency. Similarly, in high frequency, what happens? My omega square dominates 1. Like omega square will be much greater than 1. Like 10 kilohertz. 10 kilohertz means 10 to the power 3. Oh, sorry, 10 to the power 4 it will be. Okay. And its square. So 10 to the power 8. So 1 plus 10 to the power 8, I can approximate it as 10 to the power 8. That's why I can take this approximation and this approximation. So when it's one is like the in low frequency range, I can write my P1 of j omega magnitude will be 1, and in the high frequency range, my P1 plus j omega will be 1 by 2 omega. Is it clear? Is it clear? Can you just type yes or no, or any doubt you have how the low frequency and why? Okay. Okay. I'll explain it again. What happens when we analyze in frequency domain? We generally analyze for two bands, you can say. One is the low frequency band and another is the high frequency band. Okay, when you and in generally, when you plot the body diagram, what happens, there is no zero in body diagram because this is a logarithmic. Okay, log 0 is undefined. Okay, so that's why this is, suppose this is 0.001. Okay, then the next unit will be 10 times. Okay, 0.01. Then the next unit will be 0.1. Then the next unit will be 1. Then 10. Then 100. Then 1000, and so on. Okay, so we generally, what we do, we divide the body plot into two parts. One is the low frequency range and another is the high frequency range. Okay, so this part, these things, they are called a low frequency range because the frequency is very less, simple, and these are the high frequency range. Okay, so what happens is uh, when it's the low frequency range, you can see what is the square of 0.001? Okay, what's the square? It will be 10 to the power minus 6. Am I correct? What is the square of 0.01? So it will be 10 to the power minus 4. Similarly, which is very less in comparison to 1. That's why I can approximate 1 plus omega square as 1 for low frequency. Is it clear, Ishan? Then I will go for the high frequency. Okay. Similarly, when I'm talking about the high frequency, so the frequency gets bigger and bigger so fast. So it was 10 here. In the next unit, it will be 100. In the next, it will be 1000. So what happens is, when I'm talking about high frequency, so what will be the square of 1000? It will be 10 to the power 6. And of 10,000, it will be 10 to the power 8, the square. Okay. So then I can say 1 plus omega square. When it's a high frequency range, I can approximate it to omega square. Am I correct, Ishan? Is it clear? Okay. Then what happens? Then the P omega. Look at it. Here I can write this. In the low frequency range, I can write it as 1 by root over 1 because I'm approximating like that. Sorry. Okay. So I can approximate like that. Again, in the high frequency range, what happens is I can approximate this 4 omega square plus 1 to be approximate as 4 omega square. Can I do this? Yes or no, Ishan? Okay. That's why I can write in the low frequency range, the magnitude is 1, and in the high frequency range, the magnitude is 2 omega. Correct? So, the corner frequency, what the corner frequency says, I'll erase this part. Okay. The corner frequency, definition of corner frequency, you can say, the definition of corner frequency is the intersection point of low frequency and high frequency. High frequency magnet. Okay. So what happened? The intersection of low frequency and high frequency, that's why I can say at the corner frequency, at the corner frequency, P1 of j omega low frequency is equal to P1 of j omega high frequency. Can I say this? Can you just confirm? Because it is the intersection point of low frequency and high frequency, so it should satisfy both the properties. Am I clear, Ishan? Or I can explain it again. Okay. So that means what it will be? 1 is equal to 1 by 2 omega. That means my omega c, the corner frequency, is 1 by 2 radian per second. Is it clear how to calculate the corner frequency? Agam, are you able to follow this because you joined a bit late, or I'll explain it again? Okay, cool. So this is the corner frequency calculation of a transformer. Similarly, what is the second? The second question was P2S is equal to 2S plus 4. So can we calculate the corner frequency for this? If you have pen and paper, please do calculate along with me so that I will think you understand this. So the S I will take as j omega. So 2 j omega plus 4. Then the magnitude P2 of j omega. This will be nothing but 4 omega square plus 16. Similarly, low frequency, in low frequency, I can take the 16 is much greater than 4 omega square. That means it will be 16 only, say root 16, which is 4. And in high frequency, 4 omega square will be much greater than 16. So it will be root over of 4 omega square is equal to 2 omega. Similarly, the corner frequency will be where the intersection of these two, that's why 4 is equal to 2 omega c. That means omega c is equal to 2 radian per second. Is it clear? Ishan, John, or Hamza? Is it clear? It's a very simple calculation. Okay, thank you very much. So what's the answer for the first question? So it was half radian per second and 2 radian per second. So very simple calculation it was. Now the second question is the B question. Find the magnitude of the sinusoidal transfer function tend to 0. Okay, when the frequency tends to 0. Okay, here I will calculate, because this is the magnitude this is the magnitude of the transfer function. Okay, so when frequency tends to 0, that means omega tends to 0. It's very straightforward. What it will be, the magnitude will be 1 by root 1. So it is 1. Is it clear? But 1 in regular sense, but in dB scale, okay, I'll just write it in the next page. So B part, so it was 1 by 4 omega square plus 1. So when omega tends to 0, the magnitude is 1. But in dB scale, you know the calculation. In dB scale, it will be 20 log base 10 of 1, which will be how much it will be? Can somebody just say? It's very simple. The calculation, log 1 base 10. Simple question it is, very simple. Sorry Agam, I couldn't hear you. Yeah, very good. It will be 0 dB. Never forget the unit. I have told this many times. So the second, similarly for P2s, P2j omega magnitude, it is root over of 4 omega square plus 16. So when omega tends to 0, the magnitude will be how much? Root over of 16. So it will be 4 in dB. It's log 20 log 4 base 10. So you can calculate it. I have already calculated it actually. So it will come around 12 dB. Okay. You just calculate it and you will find it out. Okay. Simple, straightforward questions. Now the third C part. Okay. What does the C part say? Okay, I will just write the answer. It will be 0 dB and 12 dB. Okay. So the third question is find the phase in the sinusoidal transfer function with respect to the corner frequency. So the corner frequency is this one and this one for the P1 and this one for P2. Okay. Now I'll just write P1 of S. It's 2S plus 1 and P2 of S. It's 2s plus 4, and the omega 1c, it's 1 by 2 radian per second, and omega 2c, it's 2 radian per second. So how to calculate the magnitude and all, I had a good discussion with Agam in the last class. So the magnitude of P1 of j omega, it will be simple magnitude of 1 by 2 j omega plus 1. So it will be 0 minus tan inverse 2 j omega divided by, not j omega, 2 omega divided by 1. Okay, so the magnitude, the phase at omega c, okay, at omega c, okay, I'll just write it like this: at omega is equal to omega c, it will be 0 minus tan inverse, what is the omega c here, 2 into 1 by 2 divided by 1. Okay, very straightforward. 0 minus tan inverse of 1, which is minus 45 degree. Okay, clear, simple. The second, for the second, P2 of j omega, it's 2 j omega plus 4. That means the angle will be plus tan inverse of 2 omega divided by 4. Okay, that means the angle at j omega, at omega is equal to omega c, it will be fairly straightforward. Tan inverse of 2 into omega c is 2 divided by 4, which is equal to tan inverse of 1 is equal to 45 degree. Is it clear to everybody? Very simple questions for the frequency domain analysis. The frequency domain analysis is very simple till you get the Nyquist criteria. Nyquist criteria is a little bit like difficult to understand, but once you understand it, it's very simple. So similarly, these questions are fairly straightforward. So here it's minus 45 degree and 45 degree. So the question is, first question, everybody understood it? Or somebody has any doubt? I'll repeat. Okay, okay. So the first part says, the A part is the to find the corner frequency. Okay. So the transfer function is given simply like this. The PS is equal to 1 by 2s plus 1. So we know generally we take S is equal to sigma plus j omega, but when we do the frequency analysis, we deal with pure frequencies. There is no damping term. So that's why we only take the j omega part. So we can take P of S is equal to P of j omega, which is in place of S, we'll just put 1 by 2 j omega. Okay. So what will be the magnitude? The magnitude will be 1 upon x square plus y square. Like if this is the real axis and this is the imaginary axis, the 2 j omega plus 1 will lie 1 in real axis and 2 in j omega axis. So here, this point. Okay. So this magnitude I can calculate with this square plus this square. Simple Pythagoras theorem. So that's why. And so the magnitude will be 1 upon root over of 2 omega square, like this, 4 omega square plus 1. Okay. So forget this part. I will remove this. Okay. So what happened in low frequency? When I'm talking about low frequency, that means it's around 0.1 hertz, 0.001 hertz, very low frequency, 0.001 hertz. So when these are considered, then I can say my omega square will be very much less than 1. So I can write here 4 omega square, 1 plus 4 omega square will almost be is equal to 1 at in the low frequency. That's why I can take P omega is equal to 1 upon root over of 1 is equal to 1. Is it clear, Agam? Similarly, in high frequency means we talk about kilohertz, megahertz, you might have heard like there used to be radios, like radio jockey like Big FM 92.7 megahertz, gigahertz, kilohertz. In that range, so in that range, what happens? The omega square, if it's in megahertz, it's already 10 to the power 6. The square will be 10 to the power 12. Okay. So 1 plus omega square will be omega square only, approximate. 1 will be very less in comparison to 10 to the power 12. So in large, like in high frequency range, I can write omega square is much greater than 1. That's why my magnitude will be 1 upon root over of 4 omega square, which will be 1 by 2 omega. Is it clear? There are in frequency analysis, there are two ranges we talk about. One is low frequency and we talk about the high frequency. You can ask why we don't consider the moderate frequency, because the moderate frequency will be very less band. Like when you plot a Bode diagram, so what happens is in this, it never starts with 0. It will start from 0.001 or 0. Then each interval you will increase it by 10. So when once it's 1, then next one will be 10, next one will be 100, next one will be 1000. So the moderate frequency, it has a very less band. So that's why we generally neglect that and we consider low frequency band and high frequency band. Okay. What is the corner frequency? The corner frequency says it's the intersection point for the low frequency and high frequency. That's why at the corner frequency, I will equate the low frequency and high frequency. So similarly, I got the corner frequency. Is it clear, Agam? Okay. Okay. Then I will go to the next question. This is also very simple. If you have understood what I have told till now, you will be able to solve it by yourself. Except the third question, resonant frequency, I will explain. But you will be able. But I am here to help you out. So we'll discuss it. So it says the transfer function is 1 upon s square plus 3s plus 9. Okay. This is g of s. Let's write g of s. Then if we are analyzing it in the low frequency, it says find the magnitude in low frequency asymptote. Okay. So we need to consider the low frequency for the first question. So it's the frequency domain analysis. First thing you need to do, we need to check s is equal to j omega. We are neglecting the sigma part. So what happens? G of j omega, it will be 1 upon j omega square plus 3 j omega plus 9. That implies 1 upon negative omega square, because j square is equal to minus 1 plus 3 j omega plus 9, which I can rewrite as 9 minus omega square. This is the real part plus 3 j omega. This is the imaginary part. Till now, is it clear? Just I have put the s is equal to j omega. Okay. Then what happens? This is simply, and we need to find the magnitude. Find the magnitude in the low frequency asymptote. Okay, and magnitude plot of the corresponding sine. Okay. So this is at the low frequency. So I have discussed. So the magnitude. Let's calculate the magnitude. What is the magnitude? The magnitude of g of j omega, it will be simply 1 upon root over of 9 minus omega square whole square plus 9 omega square. Okay, 3 omega whole square, it's equal to 9 omega square. So now in at low frequency. Okay, what happens at the low frequency? At low frequency, I can say 9 is greater than omega square. I can say, okay, and that means I can rewrite it as at low frequency, it will be approximated as 1 upon root over of 9 square plus 9 omega square. Okay, very simple. Again, you can check at low frequency. Again, I can write at 9 square is much greater than 9 omega square, because low frequency means omega square is very less, so it will like 9 omega square will also be very less. So that I can write it as 1 upon root over of 9 square. So this is equal to 1 by 9. Okay, straightforward. You need to just analyze it in frequency domain. When we approximate some things, you need to analyze it. Okay, so in dB scale, because the question is asked in dB. In dB scale, 20 log 1 upon 9 base 10. So it will be negative 20 log base 10. It's 9, which is equal to, I have the answer, it's almost 19 dB. Okay, negative 19 dB. Okay, I'll write it in the other page. So it's 20 log of 1 by 9 base 10, which is equal to, not approximated, equal to negative 20 log 9 base 10, which is approximated as, okay, just approximated as negative 19 dB. Okay, this is very straightforward answer. Okay, then find the corner frequency. Who can say what is the procedure of corner frequency? I have explained thrice in this class. We need to calculate for the low frequency band, high frequency band, and equate. Okay. Yeah. Agam, you wanted to say something? Okay. Cool. Okay. My bad. I answered it. Okay. So in low frequency, we have already calculated the magnitude is 1 by 9. Okay. In high frequency, what happens? Simply, we need to analyze. We need to analyze. We are engineers. We have chosen to be like analyzing the different problems. Okay. 9 minus omega square whole square plus omega square. Okay. At high frequency, what happens is I can write 9 is very less than omega square. That means I can approximate it as 1 upon root over of omega fourth plus omega square. Again, at high frequency ranges, when it's, I am talking about kilohertz or megahertz, so 10 to the power 6, 10 to the power 4, 10 to its fourth power is 10 to the power 24, and its square is 10 to the power 12. So there is a significant gap, like 10 to the power 12, like 12 digits. So it's huge. So I can approximate it again as omega fourth is much greater than omega square. So I can write it as omega fourth, which is equal to 1 upon omega square. Is it clear? Okay. So quickly tell me, what's the corner frequency? The intersection of low frequency and high frequency? Very good. 3 watt. You must not forget the unit. It's the omega c is equal to 3 radian per second. It's not 1 by second, which is hertz, because omega is equal to 2 pi f. It's in radian. Okay, you need to keep it in mind. Okay, it's not in hertz 1 by s, it's radian per second. Okay, so this is, I got it as 3 radian per second. Okay, then what is the resonant frequency? This is the question actually. Okay, who can say what happens in resonance, during resonance? So it's in your 12th class. What happens in resonance? What we call it as a resonance? What are the effects of resonance? Can somebody just say? Hmm? Hmm? Exactly. Exactly that. When the frequency, the system frequency, it becomes equal to the natural frequency of the system, then it becomes a resonance condition. So at resonance, you can say the system becomes, the magnitude goes very high, like maximum, and the, you can say the, like it may go to unstable, unstable. It may become unstable also. So what happens is, when you say something becomes maximum or minimum, okay, there is a condition you, that also you have gone through in your 12th, which is when you, if f of x, some function is there, at its maximum its derivative is 0. So like you can say, if this is there, at the local maxima the derivatives, okay, at the local maxima the derivatives, and the local minima the derivatives are 0. Okay, you remember this concept? The at the local maxima and the local minima, the derivative, like the df of x by dx is equal to 0 at the local maxima and local minima. So I can, yeah, Agam, you wanted to say something? You remember this? Okay. Yeah. So what happens is exactly that, the, if you have gone through the lectures, the time analysis of the second order system, for the maximum peak overshoot also, if you have gone through the derivation, we do the same. The whole plot will just take the first derivative, equate it with the 0, then we get the answer. Similarly, here also, when it's at the resonance, so my system g of j omega, I'll just write it, okay, minus omega square plus 3 j omega plus 9. Am I correct? Let me check. Yeah, minus omega square 3. Okay. At resonance frequency, I can say the magnitude becomes the maximum and the derivative will be like it's the maximum. So the magnitude is g of j omega. It will be 1 upon root over 9 minus omega square whole square plus omega square, sorry, 9 omega square. So this will become maximum, this whole term. That means, that implies 1 upon that, like the, this part, this 9 minus omega square, sorry, 9 minus omega square whole square plus 9 omega square, this part will be minimum. Is this concept clear? For this to be maximum, this, the denominator has to be minimum. If this concept is clear, then the further calculation will be very simple. This is the critical part to understand. Is this clear? For, okay, so that means if this is minimum, I can write d of omega is it, sorry, I'll write it here. I will take it as a expression, d of omega is equal to 9 minus omega square whole square plus 9 omega square. This needs to be minimum. Okay, simple. That means d of omega divided by d omega is equal to 0. So let's derivative, like calculate the first derivative. What it will be? It will be 2 into 9 minus omega square into negative 2 omega plus 18 omega is equal to 0. Okay. So when you calculate it, what it will be? It will be 18 minus 36 omega, and it's minus minus plus 4 omega cube plus 18 omega is equal to 0. That means omega into 4 omega square minus 18 omega is equal to 0. This is clear? That means either omega is equal to 0 or, okay, I'll write it in the next page. So either omega is equal to 0 or 4 omega square is equal to 18. Okay, 4 omega square. Here it should not be omega. Okay. Yeah. So what I had told many times is in a frequency domain plot, when this is a logarithmic scale, the 0 omega, it does not exist because log of 0 does not exist. Okay, that's why this is out of the question now. Then that means if you equate it, omega is equal to root over of 9 by 2. Okay, this is the omega resonant frequency, which will be around omega r is equal to, I'll check it, answer 2.12. What's the unit of omega? Unit of omega, I have just said it. Very good. Radian per second. So this is the resonant frequency of the system. Is it clear? Okay. So this will be root over 9 by 2 is equal to 2.12 radian per second. So this question is clear now. Okay. So anybody has any doubt in this question? I guess no. Okay. So Agam, you had said one definition actually that okay, leave that, the resonance frequency, that was correct. Okay. So uh, now this I wanted to discuss these two questions. So I think these two are fairly simpler question than the other weeks, and using these questions you will be able to solve all the questions in the week 9 assignment. So if you have any doubt, just drop me a mail at okay. So I won't be giving the direct solution, but I will give you some hints so that you can proceed. Okay. So if you want to ask something else, you can. Otherwise, I will. Yeah. Okay. Uh, mm, okay. Okay. Agam, I'll write down this question because this is the second time you are asking the question. That means you are not clear. So next time in the next class, I will discuss with an example. Okay. Right now, I can theoretically explain you, but practical. When I tell you with a practical example, then it will be much more clear to you, and you will have a visualization. Okay. So suddenly, yes. So in the next class, I'll definitely take some practical situation, practical scenario, and explain the concept to you. Okay. Okay. So anybody has, okay, thank you. So anybody has any other doubt? Otherwise, I'll stop the meeting because I have a meeting from 7 actually. Okay. And I hope this class was useful and you have understood a bit concepts. So thank you everyone. Have a great week ahead. Okay. Thank you.